Good evening, guys. I hope I am audible. Let me just check. If my audio and video is perfectly fine, then yeah, okay. Please drop a message in the chat box so that I know that everything is fine and we can start. All right. Okay, just give me a moment. Let me fix this in. Okay. Good evening, Jerry. Yeah. So let's start. Other people will join in, and by that time we can start off, right? So yes, welcome back to Geeks for Geeks Computer Science channel. My name is Praddyumn Shukla, and in this week I'm taking live sessions on theory of computation and its Gate previous year questions, right? So today I'll be talking about a mix and a variety of questions on theory of computation. I won't be taking specific questions on, as in like in the last session I took specific questions on grammars, but today I have decided to take up a mix of questions, and I'm really sorry for starting the session a bit late because as you know, the match is going on, World Test Championships final. So because of that I was a bit late, but anyways, let's start off with the session now. And as I told you that I'll be today discussing a mix of questions. A lot of topics will be discussed in this session, right? So let's start off with the first question for today. um, Here's the first question. I have already put up the answers, but no worries. We have, let me check, just a moment. I think there's some glitch. Yeah. So this is the first question. Let me bring in the pen. Cool. So for any two languages, L1 and L2, such that L1 is context free. Okay. Let me write it over here. So L1 is given that it is context free, okay, and L2 is recursively enumerable language but not recursive. Okay, so this point is really important, that it is recursively enumerable but it is not recursive. What does it mean? Let me first write it over here, that L2 is recursively enumerable language and not recursive. Okay, so basically you have, as I told you in the classification of languages, you have a middle language which is a regular language, right? Let me write it regular only, else you will get confused with recursive. So you have regular languages which are the most restrictive type of languages, right? Then after that you have context free languages which are CFL, you also call them CFL. Then after this you have CSL, right? And then you have recursive languages. Let me write recursive language as RL, okay? And then in the outermost circle, okay, which is the most unrestrictive type of language, which consists almost of every string which is possible, that is called as the recursively enumerable language. Okay, so this is the broad classification of the languages which Chomsky had basically classified. Okay, so the more inside you go, the more inside circle you go, the language will become more and more restrictive. Okay, which means that recursively enumerable language are the most unrestrictive, then regular languages are a bit more restrictive than recursively enumerable, then and so on. So regular languages in the, so this is sorry, this is not regular, this is recursive language. Okay, recursive language and recursively enumerable language. Now what is the difference between these two languages, recursive language and recursively enumerable language? Okay, so basically let me tell you that we have something called as Turing machine, although I haven't discussed about it till now, but you can assume it just for now that Turing machine is the most powerful machine. It can probably do anything, and this is a great area of research. A lot of people are actually doing research on Turing machine to prove that there is something like everything which a computer can do that can also be done by a Turing machine. Okay, everything that a computer can do. So there is not a single thing which has been proven that Turing machine cannot do and some other machine, whether it is computer or any other machine, that can do, but Turing machine cannot do. No such work has been proven till now. Okay, so this is a great area of research. So now this Turing machine, what does it do is that there are two types of Turing machine. As I have told you, till now we had finite automata, right? We have discussed about finite automata. So how do we accept or reject a string in these finite automata? If you want to accept the string, then we reach to the final state, right? Do not worry about the question right now, we will solve it. Don't worry about the question, just try to listen what I'm trying to tell you. Okay, so in finite automata, if you want to accept a string, you will probably be trying to reach the final state, right? But if you are not able to reach to the final state, then you are not accepting the string. But how are you not accepting the string? You can't just say like that, okay, I'm not able to reach the final state, therefore I won't be able to accept the string. This happens because the finite automata halts at a state when it does not have any transition. Okay, if at the end you are reaching to a non-final state, then that basically means that the finite not in the case of finite automata, in the case of finite automata, either you reach to a final state or you do not reach to a final state. But let's suppose you have a PDA, right? So if you have a PDA, in that case either the automata is going to halt, which means it is going to stop and it is going to say, okay, I do not have any more transition on this symbol, else it is going to reach to a final state. Or we can also accept it with like we have two ways of accepting the strings in PDA, right? One is by the empty stack and other is by the final state. Okay, so similarly in Turing machine you have two options. Either the Turing machine is going to halt and it will tell that, okay, this string belongs to the language or it does not belong to the language. Okay, so you have two options. Either the Turing machine is going to halt means stop, and it will say that, okay, yes, the string belongs to the language, or it will say no, it does not belong to the language. And we have other type of Turing machine which does not halt. Okay, it does not halt, and it will never ever tell you that whether the string belongs to the language or not, and you will always be an illusion that, okay, Turing machine is right now working, it will tell me after some time, but that time will go on and you will always keep on waiting, because you do not know that after which time this machine is going to, like, I'm sure that after 3 hours it will tell me whether the string is belonging to this language or not. Okay, you do not have that upper limit. So in this case, the Turing machine may or it may not tell you that yes, the string belongs to the language or not. It may or it may not stop. Okay, but in the other type, in the first type, it is sure that it is going to stop. In the second type, it is not sure that it is going to stop and tell me whether the string belongs to the language or not. Okay, so this first type of string, which is going to definitely stop and tell me that yes, it belongs or it does not belong, they accept the recursive languages. Okay, and then as I told you, recursively enumerable languages, which are more unrestricted, the most unrestricted type of grammar. Okay, it is the most unrestricted. It does not have any restriction, like possibly any restriction which you can impose on a grammar, it does not have that as well. So recursively enumerable languages are accepted by Turing machine, that which does not halt, so by the second type. So this recursive language is accepted by the first type, and this recursively enumerable language, they are accepted by the second type. Okay, so the first type will definitely stop and the second type may or may not stop. So this is the basic difference between regular language and recursively enumerable language. Alright, now let's get back to the question. So this was a whole overview of recursively enumerable and recursive languages. So you are given two languages. First one is context free and second one is recursively enumerable but not recursive. So what does that mean? This means that you are going to lie somewhere in this circle right over here, but you will not lie inside this line. Okay, let me remove this part. So you will lie somewhere in this circle, but you will not lie anywhere inside this circle, which is the circle of regular language. Okay, you are going to lie in the outermost circle, but you will never lie inside the regular language border, because it is told that it is recursively enumerable. It is recursively enumerable, but it is not recursive. Okay, so Jerry has already told the answer. I think, Jerry, you are trying to copy from Google, I guess. That is why you solve it so quickly. But anyways, it's good that you have solved, or you have already solved this question. But anyways, let's move on. And as I told you, L1 is context free and L2 is recursively enumerable. Now I want to tell you a few properties of these context free languages and recursively enumerable language. So first thing is that is type 0, but you are saying type 1, which is correct one. I did not say type 0 or type 1. I did not say anything like that, Dhanushri. I just said that L1 is context free and L2 is recursively enumerable language. Okay, I did not say anything like type 0 or type 1. I did not even say any type. I just said that you can lie in this border at the end, but you cannot lie in the inner circle. Okay, so now what are the properties which I was talking about? First property is that yeah, so L1 is context free, and the first property is that context free languages, the first property I will tell you, context free languages or class, why would I come to class if I had to copy from Google? That's also correct. Maybe you want to solve the questions which I am solving over here, but anyways, don't take it personally, it was just a joke. So yeah, context free languages, they are not closed under complementation. Okay, they are not closed under okay, I will write it this way. So I will first tell you complementation, and then I will tell you which languages are closed under complementation and which languages are not closed under complementation. Okay, because most of the part in this options which are given, it just considers one property, which is complementation. Okay, so there is this complementation property, and what is this complementation property? Let me tell you that as well. So as I told you that if let's suppose this is the universal set, this rectangular box is the universal set, and I have a set inside a smaller set inside it, which is A. Now what will be A complement? A complement will be everything which is present in this universal set, but it is not present in A. So this part, this whole part, that will be A complement. Alright, this is the whole idea. Okay, and generally if I write L1, then L1 complement is written like this with a dash over it. Okay, now I was telling you which languages are closed under complementation and which languages are not closed under. So first thing is that context free languages, they are not closed under complementation. Remember this thing. This is a property based question. If you know the property, you will easily solve it. Okay, second thing is that recursive languages, okay, just the recursive language, not the recursively enumerable language. Recursive languages are closed under complementation. Okay, and the recursively enumerable languages, they are not closed under complementation. Okay, so one thing I want to tell you, is that what I was talking about. Yeah. So what if I say, what do I mean by saying that this is closed under complementation and this is not closed under complementation? If I say that L1 is a recursive language, let's suppose L1 is a recursive language, then the complement of this language L1, it will be L1 dash, right? Now this L1 dash, it will be recursive because recursive languages are closed under complementation. If it was context free, L1 was context free, then it may or it may not have been context free, the complement of L1. Okay, so this is the whole idea. Now let's get back to the question. So first question says that L1 dash. Okay, now if L1 is context free, if I suppose that I'll just a moment, yeah. So if I say that L1 is context free language, then tell me one thing, its complement, will it be context free or not? Just tell me this thing, L1 is recursive, yeah. Just tell me or not whether this will be context free language or not. If L1 is context free language, then its complement, will it be context free or not? Tell me one thing. And the second question, its follow up question is that whether it will be recursive or not. This is just, don't have a look at the problem statement. Just tell me one question. Question I have. I told you the properties, and now you just you have the diagram over here. Just try to solve it. That whether if L1 is context free language, then will its complement be context free? No. Basically, no means here that it may or it may not be context free. It is not definitely, I can't say that no, it will not be context free. It may or may not be context free, right? So L1 complement is never going to be context free. But can I say that if L1 is a context free language, if L1 is a context free language, then is L1 recursive language too? Okay, I repeat the question. Let's suppose L1 is a context free language, then can I say that L1 is recursive? Yes, I can. Why? Because if a language is present over here, let me change the marker, actually that will help things get more clear. So I'll change the marker first of all. Where is the pen? Yeah, which color should I use? Let's take the yellow color. So if I am present over here, yellow is not very, let me change again. Yellow is not pretty clear. Let me use black color. So if I am present over here in this circle or in this circle, then am I present inside this circle? Of course. If I am present inside the inner circle, then of course I am present inside this outer circle, right? So therefore, if a language is context free, then I can definitely say that it is also recursive. Okay, and if a language is recursive, this L1 is recursive, then will the L1 complement be recursive? Will it be recursive? Yes, it will be recursive. Why? Because I just told you that complementation, under complementation, recursive languages are closed. Alright, so L1 complement will definitely be recursive. So the first option is correct. Now let's have a look at the second option. So the second option says that L2 is recursively enumerable but not recursive. So if a language L2, as I told you, that if it is recursively enumerable, will its complement be recursively enumerable? No. Why? Because recursively enumerable language may or may not be recursively enumerable. So if it is not recursively enumerable, how will it be recursive? If I am not be able to present in the outer circle only, then how will I be? How can I say that I am present inside this inner circle? Right? So if a language I cannot definitely say that it is recursively enumerable, then I can definitely not say that it is recursive, right? So therefore this second option is wrong. The complement of a recursively enumerable language, it is not closed under complementation, so it may or may not be a recursively enumerable language. And if it is not a recursively enumerable language, then it cannot be recursive as well, right? Now the third is that L1 dash is context free. So L1 was context free, and context free languages are not closed under complementation. So L1 dash may or may not be context free. So this option is also wrong. Now let's have a look at the last option. Now L1 dash, I told you that it is recursive. Why? Because if L1 is recursive, then L1 complement is also recursive. And if L1 complement is recursively, it is a recursive language, then it is definitely a recursively enumerable language also, right? If I am present inside this circle, this black circle, then I am definitely present inside this outer circle, which is the border of recursively enumerable language, right? So L1 dash will also be recursively enumerable language, and the union of recursively enumerable language and again a recursively enumerable language, it is recursively enumerable, right? So this is fourth option is definitely correct. So first and fourth only D option will be correct, and Jerry, you told the right answer. Okay, I hope you got the intuition. If you have any doubt, please let me know in the chat box. Okay, now let's move on to the next question. So this is the question. This question was asked in GATE 2015. All right, let me change the in color again. Yeah. Now this question says that consider a NPDA which is of the form Q. Q is what? Q is the set of states. So we have Q naught, Q2. Okay, I think there is some glitch over here. Either it will be Q1, I guess it will be Q1 over here and Q2 over here. Okay, something like, don't worry about the state name, it does not really matter. Then sigma is the alphabet input symbol, which you can have, either you can have 0 or 1. Okay, then this tau is what? Tau is the stacked alphabet. They have given that tau is the stack alphabet. Sorry. And now this symbol, I do not really know how we pronounce the symbol. If anybody knows, then please let me know that as well. So this symbol is the initial stack symbol. All right, it is the initial stack symbol. So if it is the initial stack symbol, then Z is definitely not the initial stack symbol, right? Because till now I was using Z as the initial stack symbol, but over here they've given that this inverted tau, I would say, it is the initial stack symbol. So Z is not the initial stack symbol, and Z will basically, it is demonstrating over here all the elements of all the content of the stack. Okay, how? If I say that I have a transition 1 comma Z, it is going to give me 1Z. So if Z is not the bottom of the stack, then I can definitely say that this Z whole is representing everything which is present. Let's suppose I have this this symbol, the initial symbol, then I have 0, 1, 0, then this whole part, these four things, they are collectively said to be Z. Okay, so this is the whole idea. Now let's get back to the question. So the question says that you have the state function given over here. The state transition diagram is as follows, and you have to tell me which one of the following sequences must follow the string this, so that the overall string is accepted by the automata. So basically the question is that you are given this string, this is 1 0 1 1 0 0, right? And now they are asking what will be followed after this string such that this whole string combined, it will be accepted by this automata. Okay, so this is the question. Let's see who can solve it. If you can, yeah, initial stack is also taken as Z0. It is correct or not? Yes, of course it is correct. You can take anything as Z0, but over here they have explicitly mentioned that this symbol is the initial stack symbol. Then just go with that. How? It's not a very really big problem. You can consider any symbol as the initial stack symbol. It's just for the sake of understanding with whatever you are comfortable. Okay, so let's get back to the question. They have given this string and you have to tell that after this string what do I need to add so that the combined string will be accepted by this automata. Okay, now let me tell you what is exactly happening over here. So if you see what are we doing in q naught, what are we doing in q naught? If I am seeing a 0, I am simply pushing 0. If I am seeing a 1, I am simply pushing 1. And remember, this is a NPDA. It is a non-deterministic PDA, right? It is a non-deterministic PDA. Why? Because over here, two transitions are happening. One transition is this and the other transition is this. Okay, and like when you are seeing an input symbol as 1, and over here also when you are seeing the input symbol as 1, in one transition you are remaining on q0 and in the other transition you are moving to q2, right? So these are the two transitions which are happening simultaneously and therefore this is a non-deterministic PDA. First point. Now the second point, as I told you, what is q0 doing? Q0 is basically pushing the elements on the stack. Push the elements on the stack. Whether it is a 0 or a 1, it does not really matter. Okay, then after seeing a 0 or a 1 or a epsilon, okay, after a point where I assume that okay, I have seen some part of the string. So basically let me explain you. This is the whole string, right? I have put a marker over here that this part is going to be used under this self loop. Okay, till this part I am going to push the elements into the stack, and after this part either it is a 0 or it is a 1 or it is an epsilon. Three possibilities are there. After this symbol, this middle symbol, I am again going to do something. What I am doing, I am going to do something in Q2 now. Okay, so now what is happening in Q2? What is happening in Q2? In Q2, it's not Q2, it is Q1 again. I am sorry, this is Q1. So what is happening in Q1? In Q1, when the input symbol is 0 and the top of the stack has a 1, I pop it, right? So when I see a 0, when I see a 0, I pop 1. Okay, and when I see a 1, I pop a 0. How? This transition right over here. Whenever I see a 1 and the top of the stack is a 0, I pop it out. Alright. So this is the whole idea what is happening in Q1. And when after doing that, I have reached to the end of the string and the input that the stack is empty now, this inverted tau, it is telling me that I have reached till the bottom of the stack. Then I will do nothing. I will take it to another state, and this Q2 is a final state. Actually, it is the diagram might not be very clear, but you can say that this Q2 is a final state. Okay, so basically what did we do over here? Let me tell you again. In this part, I divided the whole string. Okay, this was the whole string. I divided the whole string into 3 parts. In this part, I push the elements. Okay, and in this part, I pop the elements in reverse order. Why? Because whenever I am seeing a 0, I am going to pop a 1, and whenever I am going to see a 1, I am going to pop a 0. So basically, I can also write it as the string. I can write it as, let's suppose the initial string is W. This first part is W over here, right? This first part is W. In the middle, you can have a 0, and after that, you are going to have the reverse complement, right? This complement means the ones complement. So now, let's suppose I have W equals to 0, 1, 0. Okay, or let's say 0, 1, 0, 1. Okay, then its reverse is going to be 1, 0, 1, 0, right? And now its complement that is WR dash, it will be 0 1 0 1 again. Okay, I hope you're getting it. So basically you have to reverse the string, and over here let me tell you what if the this would be very like confusing. If I say 1101, then you have to reverse the string, that will be 1011, and when you complement it, so in complementation you make all the 1 as 0 and the 0 as 1. Alright, let's see if C is the correct answer. So when you complement it, you are going to get 0 1 0 0. Okay, so this part WR dash will be 0 1 0 0, right? Either I can see a, okay, let me write it again. Either I can see a 0 in the middle of W and WR dash, or I can see a 1 in the middle of W and WR dash, or I can also see nothing. So that will be meaning that after W I directly see a WR dash. That is, I directly see a WR dash. And when is this happening? This is happening when the length of the string is even, right? When the length of the string is even. If the length of the string is odd, then you are going to, okay, no, sorry. If it is odd, I think, yeah, let me check. So the given string is of length 6, and the strings which are given over here, they are of 5. So the total is 11, right? So basically, I think, yeah. So basically, this will not be even. In this case, the length of W will be odd, and in these two cases, the length of W will be even. Why? Because what is happening over here? See, I want to, the total length of the string is 11, right? If I combine this string of length 6, and if you take any option which is given, that is of length 5, then if you combine it, the combined length will be 11, and you can get only a 11 when you will have a 0 or a 1 in the middle, right? And how will you get the middle element? Since this part, this length is of this string, given string is of length 6, and the strings which are given in the options, they are of length 5, then obviously the ending symbol of this sixth length string will be our middle part, right? So basically I have 1 0 1 1 0 0. So this part 1 0 1 1 0 will be my W. After that I am seeing a 0. After that I am seeing a 0, and then this is my middle part, and then I want to accept what? I want to accept WR dash, right? So WR dash will be what? First reverse this string, that will be 0 1 1 0 1, right? And then complement it. Okay, why are we doing a complement? Because you see, when you are comparing WWR, right? When you are comparing WWR, so let's suppose the string was 110, then whenever you saw, you first pushed a 1, then you pushed a 1, then you pushed a 0, right? And this was the bottom symbol, and after that the reverse of this string will be 0 1 1. So for every 0 you will pop out a 0, and for every, this was the middle part, right? So for 0 you popped out a 0, then for 1 you will pop out a 1. But over here we are doing the opposite. For 0 we are popping out a 1, and for 1 we are popping out a 0. That means we are accepting the complement of it. So if I write the complement over here, that will be 1 0 0, right? So this was what? 1 1 0. So whenever you are seeing a 1, you are going to pop a 0 from here, and whenever you are seeing a 0, you will pop a 1 from here, right? I hope you get the intuition. If you have any doubt, please let me know. So we were here, the complement of this will be what? It will be 1 0 0 1 0. So B is the correct answer. Okay, so Jerry, you were wrong this time. I hope you do not repeat these mistakes again, but I hope you got the whole idea of the problem. You just have to analyze what is happening in every state, and finally you have to just compare it with the string which is given to you. All right, this was the third question. Now let's move on to one more question. This question is going to be a pretty easy question because this is based on, let me show you. Yeah, this is based on the DFAs, right? So here you are given these two DFAs. One DFA is named M and the other DFA is named N. And now this question says that, let me write it again. Yeah, so consider the DFAs M and N given above or below, just do not worry about that. Now the number of states in a minimal DFA that accept the language generated by M intersection the language generated by N. So whatever the language this state M is generating intersected with the language this N is generating, right? So now let's have a look what are these two DFAs generating. This DFA, what it is seeing, as soon as it is seeing a in the end, it is moving to a final state. Okay, let's suppose I give it a string A, just A, it is going to accept it. If I give it AB, it will go from here to here, and then on seeing the B, it will come back to this state. And till the time it will not get an A, it will loop here only, right? Till the time it is going to get a B, it is going to remain here only in this state. And again, as soon as it gets an A, it is going to reach to the final state. So if I see an A, it is going to reach to the final state. And till the time I am seeing an A, no matter how many A's you see, you will remain on the final state only. Alright, so basically I have to just check that the ending part is a A. Okay, I hope you get this, how I reached to this conclusion, right? I have solved a lot of questions, and that is the reason I quickly just did that. This question, this DFA is accepting the strings ending with an A. Alright, similarly this DFA, it is checking the strings ending with a B, right? It is just the opposite of what is happening in N. So strings ending with a B, right? Till the time I am seeing a B at the end, I am going to remain in the final state. In the starting, if I see only A's, I will not move to the final state. Okay, so this is the whole idea. Now, if you want to do an intersection of the language which is generating the string ending with an A and a language which is generating a string ending with a B, then you are going to get nothing. The intersection will be an empty set, right? Empty set or empty language actually, because it will not have anything, it will not accept anything, right? So how many states are going to be present in order to accept an empty language? So Zeri is saying 2. Do we actually need 2 states? I want a minimal DFA. Think about it again. Do we actually need 2 states? No, I do not need 2 states. Why? Because I do not want to accept anything. This is going to be empty. L1 intersection L2 is going to be an empty language. I do not want to accept anything. So this will be my initial state, and this is it. I do not want to do, no matter you see an A or you see a B, I am not going to accept anything, right? So my initial state, I will only have one state, and that state will not be my final state because I do not want to accept anything. Does not matter I see an A, a B or anything. Okay, I am not going to accept the DFA. Remember, always remember, this DFA is for accepting an empty language. Accepting an empty language. Always remember this point. Okay, so we need to accept epsilon. No, very good question. We cannot accept epsilon. Remember that this language L1 equals to phi, phi means empty set, and L2 equals to epsilon. They are pretty different things. They are completely different things. Okay, this is telling me that I can accept an epsilon. Epsilon means nothing, but you are going to make the initial state as the final state. That's it. Even in that case also you will need one state only. But these two languages are completely different. it is accepting nothing. It is not even accepting an epsilon. The L1 is not even accepting the epsilon, but this L2 is accepting an epsilon at least. Okay, I hope you get this. This is, remember this thing, never ever consider these two languages as same. They both are completely different. Okay, here at least you are going to accept an epsilon, but in L1 you are not going to accept even epsilon. All right, so the number of states, minimum number of states will be 1, and let me not just remove it, but epsilon is neither ending with a nor ending with a b, right? Of course, but you want an intersection of these two languages, right? Intersection means you want to accept a string which is either which is present in both this language L1 and this language L2, right? And do you think that this epsilon is present in both these languages L1 and L2? No, epsilon is not ending with an a and epsilon is not even ending with a b, so it is neither present in L1 and it is neither present in L2. Then how will it be present in L1 intersection L2, right? If let me tell you over here with the help of the state diagram, you have L1, okay, then you have L2, right? And you want to accept this part, okay, you want to accept this intersection part, and this epsilon, it is not ending with an a and it is neither ending with a b, so it will lie somewhere around here, right? So it is not going to accept epsilon also. Okay, so the number of states will be 1. This was not a numerical type of question, I have actually made it a numerical type of question, so I hope you get this. Okay, now let's move on to the fourth question for today. This says that the number of states in the minimal deterministic finite automata corresponding to the regular expression this is the regular expression which is given, and the options which are given are 3, 4, 5 and 6. Okay, so what is actually happening over here? It is accepting the strings which are ending with a 1 0. So how you have to make a DFA which is accepting the strings of the form which are ending with a 1 0, right? So this is going to be your initial state. Whenever till the time you are seeing a 0, you will not move, you will not move, you are not going to move, and whenever you are seeing a 1, you will move to a separate state, and till the time you are seeing a 1, you will remain over here only because you want the string to end with a 1 0, right? And as soon as you see a 0, you are going to reach to a final state. Okay, and now if you see a 0, then you have to start again. If you see a 0, now again from starting you will check whether I am ending with a 1 0 or not, right? So on seeing a 0, you will go back, and if you are seeing a 1, then you just have to check again that the ending symbol is a 0 or not, so you will just move to this previous state. Okay, so this is the string which will be accepting this this is the DFA which will be accepting this regular expression, the language generated by this regular expression. So it is actually, the answer is 3. Okay, I hope this was a pretty easy question. So I was just going through GATE 2015 questions, so I just got this, and I hope you get this. If you have any doubt, again ask freely. Now let's move on to the last question for today. Now what is this question is saying? Just a moment, let me check something. Yeah, so you are given this alphabet. The alphabet has two symbols, 0 or 1, and the null or empty string lambda. So this lambda over here, it is telling us an empty string, denoting an empty string. Now you are given these non-terminals x0, x1 and n2, x2, and you have to check that the set of strings generated by these corresponding non-terminals, what are they going to be? Okay, so x1, x0, x1 and x2, they are related as follows. Okay, so this is a relation between them, and now you want to, the question is that which one of the following choices precisely represents the strings in x0, right? How do you make the DFA directly by seeing the NFA or rejects? It was a regular expression, right? It was a regular expression. Okay, let me get back to the question, and then I'll tell you how I did it. See, it is clearly seen over here that the string is ending with a 1 0, right? If I am writing 0 plus 1 star and then I am writing 1 0, okay, I am writing this. So what does this mean? 0 plus 1 star means that you can have any combination of 0 or 1 in the starting, but you have to end the string with a 1 0, right? This is it. This is I just got a condition that you have to accept, make a DFA. You make a DFA or a NFA, whatever you want. Make a DFA which accepts the strings ending with a 1 0, right? The question is now changed for me, right? I just want to make a DFA which is going to accept the strings which are ending with a 1 0. Okay, so I just got this condition and I made this DFA. Pretty simple. It will get easier to you when you will solve a lot of questions. The more you practice questions, it will get really easy. TOC is not a very tough subject. It is considered as the easiest subjects in the GATE syllabus. All right. Now, okay, I did not. I came to the thank you part quite early. Now, let's have a look at this question. So, this question, as I told you, that you are given these two alphabets and you are given these three non-terminals, and the relation between them is given like this. All right. Now, which one of the following choices precisely represents the string in x0? Okay, what are the type of strings which are being present in x0, right? So if you see, what is the minimum, there are two ways to solve this question. I will tell you both the ways. If you see, what is the minimum string which I can generate from this language? X0 is the starting symbol, of course. Okay, I want to check the represent the strings which are in the x0. For these type of questions, I first make NFA and then convert it to DFA, which is time consuming sometimes. Yes, so basically you have to decide whether you can make a DFA right away or you have to make a NFA and then convert it to a DFA. This is completely your decision and your analyzing power, whether you are able to draw a DFA right away or you cannot make a DFA directly and you have to make a NFA. Okay, but every time making a DFA and then converting it to every time making a NFA and then converting it to a DFA, it is not the right approach. Okay, at times the question, and in general I would say that the kind of questions which I have seen in GATE exam, they will, if this type of scenario comes, then you can directly make a DFA and you won't have to make a NFA. All right, so keep these things in mind. Now we were talking about the strings which are in x0. So x0, first it is generating a 1 and then it is generating whatever is being generated by x1. So what can x1 generate? So x1 can either generate 0x1 or it can generate 1x2, and I am trying to generate the minimum string as minimum as it is possible. Okay, so let me write it this way. So x0 generated 1 and x1. Okay, so if I want to generate the as minimum as possible string, then I will try to move to a place where I am going to get a terminal, and the only terminal which is present over here is this null or empty string. So I want to reach to x2 as soon as possible. Okay, so from x0 I moved to x1. I saw that I can produce 1x1, and then from x1 I have two choices. Either I can go with 0x1 or I can go with 1x2, but I will go with 1x2 because I want to reach x2 as soon as possible. So I will produce 1x2, and this x2 can directly be replaced by an lambda, or you can say an empty string. Okay, empty string, right? So the minimum string which I generated is a 1 1, right, out of x0. And just have a look, can I generate 1 0 1 1 from which of the following options? Can you generate 1 1 from it? No. The minimum string which you can generate is a 1 0 1. Okay, how? 1 0 1. There is no other option. You have to generate a 0 between these 1 and 1. Okay, these two 1, between these two 1, this 0 will be present. It has to be generated. You do not have any other choice. Similarly, even in this question, you cannot generate 1 1. You have to generate a 0 in the middle. Okay, can you generate 1 1 from this? Yes, you can. You can generate a 1 1 from this. Okay, similarly, simply how I will, this is written 1 0 star plus 1 0 star and 1. Okay, so I won't be having, in place of this star I will put 0, and I will just take out this 1 and I will take out this 1. So I can generate 1 1. Okay, now so C will be the correct answer, because I have just found out that 1 1 is being accepted. But let's check whether D is accepting 1 1. No, it is not accepting. From this part the minimum string I can get is 1 0 1, and from this part the minimum string I can get is 1 1 0 and 1. How? 1 1 0 and 1. Okay, this was one approach. I just analyzed that what is the minimum string and which option can generate my minimum string. Okay, the other way to do is that you can convert this again to a finite automata. How you are going to do that? Let me tell you. So you want to start with the x0, so you will start with the x0. All right, on seeing a 1, you are moving to x1. Okay, on seeing a 1 you are moving to x1. Let me call these state as x0 x1 only. They are not exactly x0 and x1, but this is the whole idea of converting a grammar into a finite automata. Okay, I am not going to deep, but I will just give you a brief overview. Okay, now when you are on x1 you have two options. Either on seeing a 0 you remain on x1, so on seeing a 0 you remain on x1, or on seeing a 1 you reach to x2. So or on seeing a 1 you reach to x2. Okay, and now let me remove this. This is x2. Okay, and now for x2 I have again two options. On seeing a 0 I can reach to x1, on seeing a 0 I can reach to x1, or I can directly accept an epsilon. That means I won't accept anything and this state will be my final state. Okay, because it has a terminal epsilon and I am able to reach this state, right? Now let me try to figure out the regular expression which this automata is telling me. So if you want to like get the regular expression out of a finite automata, there is a rule that the final, this is a 0, okay, yeah, this is 0, the final state cannot have any outgoing edge. Okay, so you will basically change this finite automata to this form. On seeing an epsilon you will reach to the final state x2. Let's just consider it as a temp or xt. Okay, xt means that it is a temporary state. Now temporary state, yeah, temporary state. Now I'm going to reduce it. How I'm going to reduce it? I can remove this state completely and I can make a loop over here. Okay, I can remove this state completely actually, and I will make a loop over here which will be 1 0, right? And from here I can move, take an epsilon, I can go to the last final state. Okay, so what am I doing? First I am seeing a 1, so it will be 1 dot, what am I seeing again? And in the end you also want to see a 1, right? How did I do that? Okay, let me take it back. So this was something what was happening. I wanted to reach on this state. So how am I able to reach to this state? First I have to see this one, right? So I will see this one, and after that there will be a dot. Then either on seeing 0 star, right, I want to reach to this state. Okay, so this state will either have, I will remove this, and as soon as I remove this I will get a loop over here that will give me 1 0, right? And in the end you wanted to reach to this state, right? So basically you will have 1 0, you will, like what I'm doing over here, you will have a loop of 0 and 1 0, and then it was something like this, right? 1 and 0 was present. Okay, so till this point if you want to remain on this x1, then either you can take a 1 and then again come back over here with a 0. Okay, so therefore this loop is present, this self loop 1 0, right? And now if you want to reach this state, okay, then I will remove this part, and this at least when you have reached this x1, you have to see a 1 again in order to reach this temporary state which I made, right? So you have an option of seeing as many number of zeros, this self loop, or seeing as many number of 1 0. Okay, you can see a 1 0, you can see any number of these things. This will not be a 0, you can keep a 0 star, or that is not really necessary. And at the end you have to see a 1, so that will take you to this temporary state. And when you reach this temporary state, you can take an epsilon and you can reach to the final state x2. Okay, so this will be your final regular expression, which is very similar to the option C. Okay, if even if I remove 0 from here, okay, that is also fine, because both the regular expressions are quite same. So you can put a star, and that will also give you the same thing. Okay, so this is the correct option. C is the correct option, and with this I think I'll have to end up today's session. It was a pretty long session. I hope you guys enjoyed a lot, and if you have any doubt, please let me know in the comment box, and I'll see you in the next session probably. Till then, take care of yourself, stay home, stay safe, and yeah.